My name's John Points and I'm an independent consultant based in the UK. And today I'd like to cover some aspects of selecting and using internal standards for trace organic analysis. I'll briefly explain what internal standards are, but show why conventional internal standards cannot be used to correct for LCMS matrix effects. I'll show why isotopic internal standards are the ideal solution, and then focus on some key points in both selecting and using isotopic internal standards. So let us start off with what an internal standard is, and in their conventional sense. Analytical methods for trace organic residues vary enormously, but typically they may involve a number of sequential steps, each one of which has potential for variable losses of the analyte you're looking for. Internal standards can be used to mitigate this variation. A conventional internal standard is a reference standard of something that is structurally similar to the analyte, but would never be found in the sample. So, for example, if you were looking for a veterinary antibiotic residue in meat, you might use a human antibiotic as an internal standard. You add the same amount to everything: samples, calibrants, and blanks. The idea is that everything that happens to your analyte also happens to the internal standard. It mirrors it at every stage. So, if you measure the ratio of the internal standard to the reference standard, then all variation should be compensated. Right? Well, unfortunately not, or this would be a very short webinar. The internal standard, though similar, is still a different chemical. It behaves differently. But for LCMS methods, there's also a very specific problem. Using a conventional internal standard can often be worse than using no internal standard at all. Now, to understand why this is the case and why it is such an inherent problem, you really have to understand the mechanism of LCMS electrospray ionization. So this is a stylized picture of the liquid coming out of the chromatography column and approaching the spray tip before it passes through the highly charged focusing plate on the right and into the mass detector. The liquid here is moving from left to right and picks up a charge as it passes through the tip. The charge concentrates at the tip. So in this example, positives are attracted forwards while negatives are repelled. Then, as it comes out, the liquid forms a droplet held together by surface tension. The analyte molecules are encapsulated in the droplet. This spray is heated, and so as it moves towards the detector, the liquid evaporates and the droplet gets smaller and smaller and smaller, still containing multiple positive charges. It's a delicate balance between the surface tension holding the droplet together and the positive charges repelling each other, until it gets down to a certain size, and then boom. Well, I like to think of it as a boom anyway. It's not really a boom. But the charge repulsion wins out over the surface tension, and the droplet explodes and releases individual analyte ions to pass through into the mass detector. As I said, this is a bit overly stylized, but it should be apparent that it doesn't take much to change the fine balance of when that droplet explodes, and so change the detector response. Just a tiny amount of anything that affects the surface tension or affects the charge. Anything, that is, which elutes at the same time as the analyte. And this is highly specific to the individual sample extract. If the problem is a fat, then the amount of fat in one sample extract will be different to another, and so the matrix effects are different from one sample to another. I've said that it is specific to what elutes from that column at a point in time. So different analytes eluting at different times in the same sample may be subject to completely different matrix effects. One peak may go up while the other goes down. This includes conventional internal standards. So the use of an internal standard can actually compound the matrix effects. You think you're compensating, but you're actually doubling the error. The worst thing about matrix effects is that you don't know whether they are occurring or not, particularly when comparing one sample to another. Because of the selectivity of a detector, all you see is the analyte peak. You have no idea if there was anything else there which caused the peak to be bigger or smaller than it otherwise would have been. So the only solution is to use the analyte itself as an internal standard. So by definition, it would elute at the same time and suffer from the same matrix effects. But then you need to distinguish what you've added from what you're trying to measure. And the answer is to use a stable isotope analogue of the analyte as your internal standard. So I'll briefly explain what a stable isotope internal standard is. Most natural elements exist as a mix of different isotopes, which is the same chemical but with different masses. For example, natural carbon is about 1% carbon-13. This just has one more neutron than the more common carbon-12. It's the same chemical, it just has a different mass. These minor isotopes can be refined and purified. And if you then use them to synthesize a reference standard, you get a reference standard that is the same as the chemical you're looking for, but a different mass. So it could be distinguished in a mass spectrometer. And this is a stable isotope internal standard. Typically, these are synthesized using either deuterium, carbon-13 or nitrogen-15, depending on the molecule. Either some or all of the atoms can be substituted with their matching isotope. So, for example, a reference standard of benzene has a mass of 78. If you substituted all of the carbons with carbon-13, you'd produce a benzene reference standard, an isotopic internal standard, that was identical in all respects other than it had a mass of 84. LGC offers an extensive range of isotope-labelled reference standards and the unlabelled analyte for a wide range of applications. So going back to the original question, if you now add a stable isotope internal standard in equal amounts to everything, then you should compensate for every source of variation, including those all-important LCMS matrix effects, right? Well, sorry, not quite. There are still some key things to be careful of, or it may not work out as intended. So today I'm going to discuss 4 critical aspects: the isotopic purity, the stability of the isotopic substitution, the mass difference between the internal standard and the reference standard, and the sites on the molecule where you choose to make the substitution. The isotopic purity is quite an obvious one. Although I blithely said earlier that minor isotopes can be refined and purified, this will never be 100% efficient. So there will always be a small amount of a conventional isotope, and hence you will always synthesize a small amount of a conventional molecule, which you then add to all your samples. Not a good idea when this is the very substance you're trying to measure at very trace levels. As a general rule, if your isotopic internal standards contains more than 2% of a conventional molecule, then you'll need to do some quite complex correction calculations. The site of the substituted isotope is also important to its stability, depending on your extraction method. In this example, if you're using water or acid in the method, then hydrogens are continually exchanged between the solvent and the polar parts of a molecule, including your precious deuterium, which you've carefully and expensively substituted. By the time you came to measure it, it may not be there. In this situation, it's far better to choose an isotope substitution that's embedded in the backbone of a molecule rather than in its fingernails. For example, a carbon within the ring. The third factor is a little more subtle. If your internal standard mass is too close to the conventional standard, then it might overlap with some of the minor isotopic masses in the conventional standard. The molecules containing chlorine give the clearest example, such as chloramphenicol, an antibiotic. Chlorine is mainly a mix of two isotopes, 35 and 37, and the minor one, chlorine 37, is relatively abundant, about 30% of the total. So any molecule containing chlorine would actually have two masses, a significant second molecular ion in the mass spectrum at 2 mass units higher than the main one. Chloramphenicol has 2 chlorines, so has a shadow of a shadow, one at 2 mass units higher, then at 2 mass units higher again. So you can imagine that if you made a chloramphenicol isotopic standard with 4 deuteriums, which we call chloramphenicol D4, you could not distinguish it from this shadow of a shadow at mass 325. But if you make the mass difference too big, you can also get problems. These are collectively known as isotope effects, a nice label because they're complex and not always fully understood. The underlying cause is that it was not quite true to say that isotopes are chemically identical. They're not. The atoms are slightly different sized, which means that bonds are of slightly different length, both bonds within the molecule and hydrogen bonds that retain the molecule on the chromatography column. The result can be that the internal standard has a slightly different retention time than the analyte. In fact, the worst case I've seen was nearly a minute's difference. On LCMS, this is disastrous. It means you've lost all of the advantages of using a stable isotope and may as well be using a conventional internal standard. But although isotope effects are structurally related, it's a general rule that the greater the relative mass difference, the greater they are. So it's important to choose a stable isotope internal standard that's no heavier than it needs to be. Back to the example of chloramphenicol, you typically choose a D5. Finally, you have to consider what you're intending to do to the molecule in the mass spectrometer and how this will affect the atoms that have been substituted. The labels are useless if they do not actually end up in the fragment that you want to measure. Back to our chloramphenicol example again, and looking at the top arrow, you may be intending to fragment it in the mass spectrometer and monitor for mass 152. That's the fragment in the top square brackets. So, if you wanted a D5 internal standard, the structure on the bottom left is ideal. When it goes through the same fragmentation, all of the deuteriums are left on the fragment you're looking at. So you still get your 5-unit mass difference between the fragment from the reference standard and the fragment from the internal standard. I had to think of a hypothetical molecule to illustrate the counterexample. Now this is the same mass spectrometry conditions, looking for the same fragment. But if you had the D3 positions in the molecule on the bottom left, then none of the deuteriums make it through to the fragment you're looking at. So there's no way of distinguishing your internal standard from your analyte. Okay, so finally, once you've selected your internal standard, I'd like to just mention 3 important considerations when using it. Keeping the concentration approximately equal to the expected analyte concentration, adding it early, and only applying the internal standard correction to the appropriate analyte. The first point arises because neither the internal standard nor the analyte are isotopically pure. I've already said that the internal standard might have up to 2% isotopic impurity. If the concentration of the internal standard is too high, then this becomes increasingly significant. But similarly, the analyte also contains a small natural amount of the isotopic analog. So if the analyte is too concentrated relative to the internal standard, then this becomes significant. These relative contributions can be mathematically modelled, but it's fairly obvious that they're only insignificant, and therefore the calibration remains linear, when the concentrations of the internal standard and the analyte are about equal. Secondly, as with any conventional internal standard, if your internal standard is to mirror every step in the procedure, then it must be added right at the start. This includes extraction. If you add the internal standard onto the surface of your sample and wash it straight off again with the extraction solvent, then it is not mimicking the difficulties in extracting the analyte. So as with any spiking, the internal standard needs to be in a solvent that's absorbed by the sample. There's no point adding an aqueous solution onto a sample of fat. Then it needs to be left for the internal standard to absorb as much as possible whilst the solvent evaporates. As a general rule, you should be adding less than 200 microlitres, but this will still take 30 minutes or more. Only then do you add your extraction solvent and start the procedure. And finally, remember that for LCMS matrix effects, the internal standard is only applicable to its own matching analyte. Be very careful about using one representative internal standard to cover a whole class of analytes. I know that this compromise is inevitable. For a multi-residue method, it's impractical to have an entire matching set of internal standards, so all laboratories will break the analytes down into groups and choose one member from each group for an isotopic internal standard. But if you have any analytes within the multi-residue suite where accurate quantification is absolutely critical, then as a minimum each of these should have its own matching internal standard. It's rare to find a set of real data that conveniently illustrates all of the theoretical points that you make in a lecture, and so I really like this set of results produced by LGC about 10 years ago. These are the results of 6 replicate sets of analysis of a blood serum sample containing testosterone. The sample had been accurately prepared, and so the true value was known to be 2.1 nanograms per gram. Each set of measurements used a different calibration method for the LCMS-MS, but otherwise the methods were identical. Working backwards, set 6 used just a testosterone reference standard prepared in solvent. Set 5 used a conventional internal standard, nandrolone in this case. Set 4 used a testosterone D3 isotopic internal standard. 3, 2 and 1 are then similar, but they're matrix matched. This means the standards are prepared in an extracted blood serum rather than in solvent. Now the center point of each set shows the average result, while the bar shows the spread. You can see on set 5 the LCMS matrix effects you can get from using a conventional internal standard. But at least in this case, the wide spread of results would give an indication that something was wrong. More concerning is set 6. The matrix effect bias is incredibly consistent. If you did not know the true value, then you would assume that you had a very good and accurate set of results. It's only when using the isotopic internal standard, sets 1 and 4, that we get both precision and accuracy. So, in conclusion, I would say that isotopic internal standards are a little bit more than just an invaluable aid. In the case of LCMS, they can be essential for accurate results, but they're not a panacea. If you do not apply some real expertise to their synthesis, selection and use, then results still might not turn out as intended. These decisions depend upon the specific application and analytical method. With the right choices, you can get excellent results.